So I really think we'll get through it.
Are we around 12?
Yes. Yep. Aqueous solution stoichiometry. Has anybody seen Daniel today?
Yeah, he was doing a test.
Okay. All right. So, we most recently talked about solution concentration, and then more about solution concentration where you can go back and forth between moles and volume and that sort of thing, or grams and volume. And before that, we talked about stoichiometry. So now we're going to blend the two. We're going to talk about stoichiometry, balanced chemical equations, stoichiometric coefficients and ratios, and the fact that actually one of the reactants, if not all of the reactants, are aqueous solutions. So this actually is a figure from your textbook, and more recently, like I said, we've been using molarity to go back and forth between volume and moles. Well, if you have two reactants, I'll call this R1 and R2, or a reactant and a product, I guess it could be, we can go back, once we have moles, we can obviously go back and forth between moles of something to moles of something else using a stoichiometric ratio. And we already kind of talked about all these other ways. Okay, stoichiometric calculations involving molarity, and molarity is our ticket to go back and forth between moles of a solute and volume of solution. So broadly speaking, the two types of stoichiometric calculations involving aqueous solutions we run into are this. One is that we are given enough information to find the molarity of something else. Now, I keep saying that something else would be a reactant, but it could be a product, the molarity of a product. So a specific concentration of something involved in the reaction. The other general type of calculation, stoichiometric calculation involving aqueous solutions, is that we come up with how much volume of a reactant or product do we need to go ahead in the reaction or have the reaction occur. What's the volume? So those two, concentration or volume. So if you guys, it's almost like a chant. It's like if you have one equation, you can have one unknown and solve for that one unknown. If you have two equations, if you have two equations, you can solve for two unknowns. Three equations, solve for three unknowns. So we're just dealing with one equation, one relationship. So, but we have three different, one relationship, I guess I would say. We have three things that go into this relationship. We have the moles of solute, the volume of the solution, and that ratio would give you the molarity, solution concentration. So this is to say, of these three things up here, if you know any two, you can find the third one. And that's all we're going to make use of. And you guys have been doing problems like that this week. All right. So, for instance, if we have sulfuric acid, H2SO4, reacting with sodium hydroxide, NaOH, notice this is balanced actually to form sodium sulfate and water. This is the sort of problem that would involve aqueous solution. Notice the AQ. And it's also stoichiometric problem. So let's see how this works. What I usually do is kind of like I did for my just regular stoichiometric calculations. I took the information that was known and I put it underneath the balanced equation. So what volume of 0.235 molar NaOH? So I'll find my NaOH, and under my NaOH, I'm going to put question mark volume. What volume of NaOH? Notice that also I know the molarity of the NaOH, 0.235. I'll go ahead and just put a big M there, but I know that big M means moles of NaOH per liter of that NaOH solution is needed to react with, now we're dealing with H2SO4, so I'll put this information under my H2SO4. With regard to H2SO4, I have 35.0 milliliters, and the molarity of my H2SO4 is 0.108 molar. And I always tell students, of those two, and H2SO4 and NaOH, of course we know more about the H2SO4. So here when we work this problem on the next few slides, our first step is going to be we're going to start with H2SO4 and we're going to come up with moles, specifically moles of H2SO4. Then we're going to use stoichiometric ratio. I don't know how I want to do this. Oops, I guess I should put it this way. Moles of H2SO4. Then we can get to moles of NaOH using the stoichiometric ratio. Goodness. And then once we have moles of NaOH, we can use moles of NaOH and now molarity to get to volume. So I'm just going to kind of take my moles of NaOH, my 0.235 molar of NaOH, and I'm just going to draw, I'll put a number 3 there though. It's 3 steps. First step, moles of H2SO4. Second step, moles of NaOH. Third step, go ahead and use the moles of NaOH and that molarity to get to volume. That's pretty messy. So notice, like I've done before, and I probably wouldn't do the whole, I probably just would say moles of H2SO4. And we've been doing this sort of calculation before. We're going to take the volume, 35.0 milliliters, and we'll go around the room. So Benny, we'll pick on you. How do we get from milliliters to liters?
1 liter over 1,000 milliliters.
I'm liking it. You got it. 1 liter of 1,000 milliliters. And I know it says of solution, but sometimes I don't put the SOL apostrophe in, maybe like I should or shouldn't. Okay, so that gets us to liters of solution. So what do you think, Allison? How can we use its molarity to get to moles? On the previous slide. Actually, it's molarity. So the molarity was given 0.108. Yeah, you're fine, 0.108 molar.
So it would be 0.108 mole over.
Yep, you got it. 0.108 mole over 1 liter. And again, I wouldn't necessarily put H2SO4 because I labeled my calculations. So very good. I think that would get us. So how many sig figs do we need, Madison? I'm liking 3. So 3 sig figs, you're looking at 0.00378 moles, or moles of H2SO4. Now, I think I might have mentioned this before, but this is what I've been calling the label, L-A-B-E-L. If you don't label it, then you're probably going to have to make sure you use H2SO4.
How is this different from what we did yesterday?
Like in lab, or you mean Wednesday? You mean?
Oh yeah, Wednesday.
Wednesday in lecture?
Yeah, like the homework.
Yeah, it's very similar. It's almost exactly the same. It should be the same. The difference is that we're going to link. We're looking at 2 species. Now we're just looking at 1. So now we know moles of H2SO4. Now we're going to go to moles of NaOH. So back to you, Benny. So this is going to be my first term. Okay. So how can I use this as a stoichiometric ratio to get to moles of NaOH?
You're going to have 2 moles of NaOH over 1 mole of H2SO4.
Exactly, 2 moles of NaOH over 1 mole of H2SO4. Exactly. So I would probably just call this moles of NaOH. Wow. Okay. So how do we round this, Allison? 3 sig figs, exactly, because the 2 and the 1 are exact. Perfect. So you're looking at 0.00756 moles of NaOH. So this would be up to step number 3. So I'll put you on the spot, Madison. What do you think step number 3 was? Wait, I know, I got it. We're going to start with that term. Now, step number 3, can you help me use the molarity of the NaOH to get to volume?
Would it be 1 over the 0.2?
Yep, It'd be the 1 liter over the 0.235 moles. Perfect. Yeah, and this probably is just like what you guys did for your homework. Yeah, great. I can't remember, Benny, how would we convert it to milliliters if we wanted to?
1,000.
Yeah, 1,000 milliliters over 1 liter. You got it. But I can't remember if we're going to do that. I guess we are. Now, you might cry foul because I don't think the problem said what volume in milliliters. I don't know. Okay. So if you just stopped at liters, that would be golden. Okay, cool. And 3 sig figs. So you're looking at 32.2 milliliters of solution. And sometimes, depending upon what mood I'm in, I'll take this volume and I'll go back to that balanced equation where I put stuff under it, and where I said question mark volume next to my NaOH, I'd put 32.2 milliliters, just because I feel so good about it. That's it, kind of a 3-step sort of thing. Let's do another one. The same reaction. That says, what is the concentration of H2SO4? So under my H2SO4, I'll put it on the second one. I'll put question mark M for molarity for my H2SO4. If 25.0 milliliters of the solution. Now, you might have to do a few of these to connect up, but when they say that, that is the 25.0 milliliters goes with the H2SO4. So 25.0 milliliters of the H2SO4 solution. We're trying to find the molarity. By the way, there's a great, you guys used the 10 ml pipette a few times. There's one that's a little fatter, 25 milliliter. So that one's kind of common. Of the solution required, then I've got 2 things. I've got a volume, 27.7 milliliters, and I've got a molarity, 0.444 molar, and those are both associated with the NaOH. So I'm going to find my NaOH. I'm going to put 27.7 milliliters, and I'm going to put 0.444 M for molar. I'll try not to make this one as messed up as the other one. So do you see where what I know most about is my NaOH? So I'm going to use the volume and molarity to get to moles of NaOH, and I'll call that step number 1. And then I'm going to use stoichiometric ratio to get from moles of NaOH to moles of H2SO4 using, I'll just put ratio from the balanced equation. And then once I have moles of H2SO4, see if you buy this, all I need to do then is take the moles and I'm going to divide it by, I'll put divide by this volume up here to get the molarity. The moles divided by the volume is molarity. What is molarity? It's moles per liter. What will I have? I'll have moles per 25 milliliters. So I have a little bit of fixing to do. So that would be my step number 3. So my ratio was 2, and this thing over here is 3. All right. So I think we were at you, Allison. So how can I go for the moles of NaOH starting with my volume? What do I have to do before I can use molarity?
1 liter over 1,000.
Perfect. 1 liter over 1,000 milliliters. Exactly. Now, Madison, I'm ready to use my molarity, which was that 0.444 molar, to get to moles. What does that look like?
So it would be 1 over.
We want our liters to cancel. So what 0.444 means is?
So it would be 0.444 over 1 liter?
Yep, 0.444 moles, or moles of NaOH over 1 liter. Perfect. Now my liters cancel. And Benny, how many sig figs? 3. So you're looking at 0.0123 moles of NaOH. That was step 1. So what's step 2, Allison?
Find the moles of H2SO4.
Yep, find the moles of H2SO4. Oh, did I skip Betty? No. Did I?
Wait, sorry.
I can go back.
I said
Sig figs?
yeah.
Okay. So Allison says we're going to go use so I'm going to put you on spot, Madison. We're going to go from moles of NaOH to moles of H2SO4. So how can we use a stoichiometric ratio to make that happen? Like the balanced equation, this is 1 mole of H2SO4 reacts with 2 moles of NaOH. So how can I use that information to put a ratio here to make moles of NaOH cancel, be left moles of H2SO4?
Would be 1 H2SO4 or 2?
It would be, except don't forget to put the word mole. 1 mole, you got it, 1 mole H2SO4 over 2 moles of NaOH coming from a stoichiometric ratio from the balanced equation. Perfect. 3 sig figs. So around 3 sig figs, you're looking at 0.00615 now moles of H2SO4. That was step number 2. So, Benny, do you remember what we're going to do to finish up?
Yeah. So we're going to have the moles of H2SO4 over 25.
We are. Very good. Yep, we're going to take that 0.00615 moles of H2SO4 over the 25.0 milliliters. That's what we had for H2SO4. That was our volume. So, Allison, how do we fix it and get liters in the denominator?
1,000 milliliters over 1 liter.
Yep, 1,000 milliliters over 1 liter. And that will give us moles per liter. And then, Madison, how are we going to round it? 3 sig figs. I agree. So you'll probably, by that point, I'm just ready to get on with a new problem. So I usually just put the big M. So 0.246 molar H2SO4. What that really means is 0.246 moles of H2SO4 per liter of that solution. All right? So it's just like doing solution concentration with like a stoichiometric calculation in the middle. We're going to do a follow-up specifically to the one we just did. And the follow-up looks like this. What is the concentration of Na2SO4, sodium sulfate? So question mark, when it says concentration, in this sort of problem, we're talking molarity. So question mark molarity. And in parentheses, it reminds you what we just did. We said that you had 25.0 milliliters of H2SO4, and we said we had a volume of 27.7 milliliters of NaOH, and with regard to the NaOH, we had 0.444. It was present in the concentration of NaOH is 0.444 molar. Now, the catch here, and I'll kind of show you the things you know most about. Well, we knocked out the molarity, didn't we, most recently, of the H2SO4. But what we're going to do is we are going to take these, we're going to use the molarity and the volume of NaOH to get to moles. We did that before, so actually I'm not going to reinvent the wheel. Moles of NaOH. We're going to go back and we're going to pick up that number. We're going to use, this is similar as I think about it to what we did before. From once we have the moles of NaOH, we're going to go for the moles of H2SO4, or excuse me, SO4. And then what we did before for the H2SO4 is we took those moles and we divided it by the volume. The only catch here is the volume, I'll just put volume, I should put it this way, of product The volume on the product side is this volume plus this volume. Oops, sorry, go back. So the volume on the product side is the volume of your two reactants. So here in a minute, we're going to take 25.0 plus 27.7. That's going to be our soup that those moles are running around in. So we're going to take these moles divided by that total volume to get the molarity of your Na2SO4. So here we go. I think we're back up to you, Benny. I think. Help me out. How do we use the stoichiometric ratio between the NaOH and the Na2SO4 to get to moles of Na2SO4?
1 mole over 2 moles.
Yep, 1 mole over 2 moles. 1 mole of Na2SO4 over 2 moles of NaOH. Perfect. So Allison, sig figs? 3. Yep. So you're looking at 0.00615 moles of Na2SO4, which if that seems familiar, it's probably because it should, because it's that the same moles that we came up for the H2SO4 actually see they're in the same stoichiometry. 2 to 1, 2 to 1. So anyway. So Madison, what was our next step? It would be kind of the third step-ish. Now we have moles of the Na2SO4, and we want molarity. What do we divide moles by to get molarity? Liters, the volume, exactly. So that's what we're going to do. But we need to add those two volumes together, the two volumes of our reactants. So we had 25.0 milliliters of H2SO4, 27.7 milliliters of NaOH. So the moles we just came up of our Na2SO4 are swimming around in 52.7 milliliters. So like Madison said, we're ready to go for the end result. So now here to knock out the molarity of our Na2SO4, we're going to take the moles we had in the previous slide, 0.00615 moles of Na2SO4, and we're going to divide it by 52.7 milliliters of solution. So Benny, how do we fix this to get moles per liter instead of moles per milliliter?
1,000 milliliters over 1 liter.
Yep, 1,000 milliliters over 1 liter. Perfect. I'm going to reserve the sig fig question for you, Allison, because it's 3 sig figs, right? Okay. So 3 sig figs would give you a value of 0.117, and the units for that would be molarity, or moles of Na2SO4 per liter of solution. It's kind of a different twist to a solution, aqueous solution stoichiometric calculation.
So for the test, like, are you going to want us to write it that way or the other way?
Either of these two ways would be great for the test. Yep. And probably in my answer key, I'm probably going more for the big M. But I think I've said it before that if you're working it, if you need to use molarity in a problem, this is what I'll be looking for in the problem to make your units cancel. Yeah. All right. So one of the last things I want to talk about is what you guys are doing next Thursday. Okay. So you guys are going to be doing a titration. It's kind of fun. So the thing about the problems we just looked at, one of them was all of them were something about volume, 27.7 milliliters. Like, how do you get 27.7 milliliters, okay? And the answer is drip, 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 okay? So it's a piece of glassware, I think you've looked at it before, and coming up with a picture that looks like this. This is a burette, and drip, 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 drip is like this. You basically let it drip out of here. Now, this would be a bad thing because this is called a stopcock. This thing right here, it's plastic. This is glass and glass, or sometimes plastic and glass. But if it's like horizontal with the tube, that means it's wide open. Okay, and it's counts like your gas jets. If it's perpendicular, it's all the way closed. If it's anything other than perpendicular, you might have a little bit of, we call this the titrant in the burette leaking out. Okay, a couple ways of spelling burette. So I would take either one. So the titrant is what's in the burette. Okay, but in the problems we've been working, you have two things that are liquid, right? You have like liquid H2SO4 and NaOH. Okay, so one would be in the burette and the other one would be in like a little beaker or flask underneath the burette, and that's called the analyte. So titrant is dripping into the analyte. So here we have a person, I like his goggles. I don't know where he got them from, but I want them. They're orange. So notice, and you'll be able to do this next Thursday if you want, you can have like a little funnel to help you get the titrant into the burette. So he's got the stopcock there, and that's about it. So that's the titrant, and he used an Erlenmeyer flask to have the analyte in. Okay, we can use, I think you guys are going to use Erlenmeyer flasks too. So one of the things we've been talking about here is like if you have something with gradations like this, like the burette, you need to be able to estimate between the marks. So, and if you're like me, reading burettes just drives me nuts. So I have to read them and then reread them and kind of consider, because they go backwards. So these major units are milliliters. So we have 3 milliliters, 2 milliliters, 1 milliliter. And actually then as you dispense it, as you dispense the fluid from the tip of your burette, this mark goes down and the numbers increase. Okay. So for instance, all right. So if this is 1 mil, this 2 mil, let's see, this would be 1 mil. So that means like this one right here is 1.5 milliliters. Okay. This right here is 1.2 milliliters. Well, I'm actually on the other side of 1. So this would be what, 0.5? Does that make sense? 0.5 milliliters? So this is actually 0.4. And to me, and you have to estimate between the 0.4 and the 0.3. So I'm liking like 0.3, hard to tell, from 8 milliliters. Okay, that's what I would say, and we're going for the water that we'll be using forms a curve like that, so we're going for the bottom of the curve. Okay, so 0.38 milliliters. 1, 2, I know it's hard. 1, 2, 3, and then the bottom, 0.38 milliliters. So, like this caption says, we're able to read to the nearest 100th of a milliliter. And then, so say you drip some out. So this would be our, actually this works out good. I'll make this my initial burette reading, it's my initial reading. And let's say we drip it out and we end up with something kind of right down here between these two major marks. So that would mean our final reading. Okay, so let's see, how does that work? So this is 2. This major mark right here would be 2. This is 2.5, so I'm liking 2.35. So we always will have a final reading and an initial reading. So how can I get the volume dispensed? Subtraction, exactly. So the volume in this case is going to be, it's always the final minus initial, so it's 2.35 minus 0.38. And units are milliliters. That's a 3. Yep. Daniel!
I was in history and the exam took an hour and a half.
Oh, well, welcome.
And he kind of foreshadowed that it would take probably that long.
Well, we figured something was up, but as you can see, you are.
Where's everybody?
We're not sure. We were just having a party till you got here, so no, okay. So you're just in time for video.
Sweet.
So this idea of having two things react. So you have something in your burette and you have something, your analyte waiting down here. So you have your titrant and your analyte. So first off, in order for a titration process like this to work, you need to be able to dissolve the analyte, okay, in liquid. So that's the aqueous sodium hydroxide, aqueous H2SO4. The other thing is, in order to do the calculations we did before we looked at this example, we need to know the balanced equation. So the balanced equation is the stoichiometry. Stoichiometry and balanced equation means the same thing. Okay, how do they react, relatively speaking? The other thing is it can't be slow, because the whole, and when you'll see this on Thursday, is when you drip in, you'll be looking for a pink color change. So when you drip in your titrant into your analyte, it can't like take a couple of minutes to react. Otherwise you'll be like, oh, I'm not there yet, and you'll drip more titrant in and you'll what we call over titrate. So it has to be fast. We generally think that reactions happen just like that. Not so. The other thing is the reaction needs to go to completion. We talked about reasons that you don't get 100% yield is sometimes reactions go backwards. They're called chemical equilibria. So that kind of messes with your stoichiometric calculation. That won't work with this sort of approach of a titration. The other thing is you need, I mentioned for you guys Thursday, you'll be dripping looking for a pink color change. You need some way to know that you're done, your titration is over. When I say your titration is over, that simply means that basically the moles or whatever that you had in here as the analyte, they've all been used up with the titrant that you've added. That means you're done. It's like going, it's like making cookies and you have the exact right amount of all the ingredients to make as many cookies as you can. You're going to run out of everything at the same time. Okay, that's what that looks like, which doesn't happen very often. So I mentioned the pink color, okay, that you guys are going to be looking for. That's actually when your ingredients, if you're making cookies, when all of your ingredients are used up, okay, that's what we call the equivalence point. Okay, all your reactants are all done, okay. The equivalence point is the actual thing, but the end point is what you see it as. The difference is, think of it this way, the equivalence point is the real deal, but the end point is probably what it says as the investigator will report. So it's to mean that you probably can't see exactly when you ran out of all of your ingredients. This italic says, we hope that they're the same, but not necessarily. It's funny because we abbreviate equivalence point EP. Guess what we abbreviate endpoint? EP. So if you see EP, that's equivalence point or endpoint. So now here's the deal. This catches a lot of us who do titrations. In order to get that pink color that you guys are going to get next Thursday, you have to add another, it's an indicator. It smells great. It's phenolphthalein. So you guys are going to put something in there that's going to make the color change. So the problem is that if you don't put in that phenolphthalein, it's never going to change colors. So you have to be dripping titrant, and you're like, I think I'm past the equivalence point or endpoint. So anyway. So it needs to usually be something visual with an indicator. The other approach, and I did only one little brief undergrad research project at UNI, and it dealt with conductivity. So what you do there is you take your solution down here and you basically measure conductance. And you're looking at an inflection point in your conductance. Potentiometrically and conductance mean the same thing. So, but we're going to use a visual indicator. Those are more common. So, let's see. Do we already watch this one? Well, I don't know. Yeah, on the board, I'll draw my burette. My burettes do not look very good. They look, I don't even know if they look better than my beakers. Okay, so here's my burette. Okay, here's my stopcock. Oh, there's my stopcock. And then here is, and like we've seen before, this is my Erlenmeyer flask. Erlenmeyer flasks were great to have your to titrate into because they kind of prevent splashes and all that. So this is my titrant, and this is my analyte. And for whatever reason, it probably has to do with using phenolphthalein. Whatever, titrants oftentimes are your bases, but not always. And then if you're doing acid-base titration, that would make your acid your analyte. So this says we grab a pipette that's 50 milliliters, and we go ahead and use a pipette to get 50.00 milliliters of CH3COOH, acetic acid, is our analyte. And it says we're going to titrate it with NaOH. Specifically, we know the molarity, 0.1150 molar. Okay. So what we've done before is we kind of write those things underneath where they go. So 50 milliliters of acetic acid. From acetic acid, 50.00 milliliters of acetic acid. I don't know the molarity, but I know that, yeah, I do, don't I? No. Anyway, sodium hydroxide is 0.1150 molar. And you'd be like, wait a minute, I don't have enough information to do a problem yet. Well, it goes on to say that when we titrated, I kind of showed you a little bit about this initial versus final. Our initial burette reading was up at 0.48 milliliters, and after we dispensed to the endpoint, equivalence point, we got it, our burette read 23.90 milliliters. How did you say I could get the volume dispensed? By subtraction, exactly. So now we're kind of looking like one of those other problems we did before. So I can use this information to get to volume. Volume from subtraction. Now, are we looking pretty good? So now I have volume of NaOH, molarity of NaOH. I can get to moles of NaOH. And I can use moles of NaOH to go to moles of CH3COOH using the ratio. And then I can use moles of CH3COOH, and if I get take this moles and divide it by that 50.00 milliliters, that will give me to molarity. Oops, sorry. And I didn't even read the question yet, did I? Using the information previous titration, calculate the concentration of acetic acid. So under acetic acid, under the CH3COOH, I finally put N is equal to question mark. So we do have kind of a three-step approach. Well, 4 if you count. You have to do the difference here, and then use the volume and molarity to get to moles of NaOH, and then use the moles of NaOH to get to moles of CH3COOH, and then use the moles of CH3COOH divided by that volume to get to the molarity of that CH3COOH. So staying organized can help in working problems. But here's how we get to the volume that was dispensed. We always take the final burette reading, which was down here at 23.90 milliliters, and from that we subtract the initial burette reading, the 0.48 milliliters. And since we are subtracting, we go with decimals, not sig figs. This is a good example. If we'd gone with sig figs, we don't have 2 sig figs. But we're subtracting. We don't do as much subtraction in working chemistry problems. 23.42 milliliters. So if I was diagramming this out, I would take that 23.42 milliliters and I would slap it underneath my NaOH, because that's what it is. It's the NaOH volume. Now it becomes similar to what we did before. So, Benny, help me out. So I want to go to moles of NaOH, use the molarity, but since this volume is milliliters, what do I have to do?
1 liter over 1,000.
Yep, 1 liter over 1,000 milliliters. Perfect. This is my moles of NaOH. So, Allison, how do I now use molarity, which was that 0.1150, to get from liters to moles?
0.1150 moles over 1 liter.
Yep, 0.1150 moles over 1 liter. Perfect. So Daniel, how many sig figs do we have?
4.
Well, I'm liking 4. I'm excited. 4 sig figs. Yep. So at that point in the problem, you're looking at 0.002693 moles of NaOH. So Madison, the next thing is going to be to go now to moles of NaOH to moles of CH3COOH using the balanced equation, making a ratio. So what does that look like?
So you put 1 mole CH3 over 1.
You got it. 1 mole of CH3COOH over 1 mole of NaOH. I'd ask how many sig figs, Benny, but I think you're fine with 4, and I can do that math. Okay, so yeah, we have the same number of moles of CH3COOH as moles of NaOH, which is that 0.002693. It's once you do enough stoichiometric calculations and solution concentrations and aqueous solution stoichiometric calculations, sometimes you skip a step like this. Don't skip a step like this. Okay, so Allison, do you remember what did we say we would do next? Or did I say it? What do you think? Now he doesn't. So we're gonna, well, we want molarity. So do we have the volume of the CH3COOH?
50 mole.
So if we just take those moles and divide it by the 50 milliliters. So 0.002693 moles of CH3COOH divided by 50.00 milliliters of solution. That was our aliquot. So Daniel, molarity is moles per liter and not moles per milliliter. So how can we fix that?
Put 1,000 liters over 1 liter.
Yep, 1,000 milliliters over 1 liter. Perfect. And then Madison, how are we going to round this?
4 sig figs.
4 sig figs. So I get 0.05387, and I would probably just put a big M, CH3COOH. What it means is 0.05387 moles of CH3COOH per liter of that solution. So the burette and the Erlenmeyer picture wasn't really needed, but it's stalling sometimes, and a picture can kind of be like, oh, that's what that looks like. Dun, dun, dun. So this homework, I couldn't leave you with a Friday with no homework. So this homework is due Monday. And yeah, we'll be finishing up the material sometime early next week. Maybe we should just have our Unit 2 exam next week. No, I'm just kidding. No, that's no fun.
I'm fine with biology next week.
Oh, that's right. Ooh, those 8-week classes, they can be
Yeah.